Hello, everyone. Welcome to today's stream. Hopefully, everyone had a good weekend. Today, we are going to be going over some more coding problems. No AI, just raw code. And we'll also be getting into some containerization, figuring out what it is, why it's useful, why we need it. And hopefully, if there's some time, we'll get into some Docker and other real examples. My focus for this is that we'll be able to build up our ability to even test some of these containerizations that are out there and work on some vulnerabilities that might be available to us to break out of the container and do some real red teamy stuff. So without further ado, let's go ahead and spin up our coding challenges for today. I think we're going to start. There we go. Where we left off. All right. So this is lesson 9 of Codility, focusing on maximum slice problem. No better way than to just jump right in, right? All right. We'll go ahead and skip the tour. We've done this a few times. Make sure we switch to our favorite Python. Okay. So, an array A consisting of n integers is given. It contains daily prices of a stock share for a period of n consecutive days. If a single share was bought on a day P and sold on day Q, where 0 is less than or equal to P, less than or equal to Q, less than N, and the profit of such transaction is equal to A indexed on Q minus A indexed on P, provided that A indexed on Q is greater than or equal to A indexed on P. Otherwise, the transaction brings a loss. For example, consider the following array A consisting of 6 elements such that A is 0 through 5. We have 23,171, 21, 21, 21, 21, 21. So if a share was bought on day 0 and sold on day 2, a loss of $2,048 would occur because A index 2 minus A index 0 gives us this minus that, gives us our accurate loss. If a share was bought on day 4 and sold on day 5, a profit of $350 would occur because A 5 minus. Okay, so simple math. We like that to start off. It is Monday. Hope everyone's caffeinated and hydrated. This one's, oh boy, this one might be getting into some stuff. So we need to write our function, our definition solution, that given an array A consisting of n integers containing daily prices of a stock share for a period of n consecutive days returns the maximum possible profit from one transaction during this period. The function should return 0 if it was impossible to gain any profit. So it sounds like we want to go through this whole array, figure out what is the difference between the consecutive days, and make sure that we're walking away with some money in our pocket. So let's see, the function, given our example array, the function should return $356 as explained above. Write an efficient algorithm for the following assumptions. N is an integer within the range 0 to 400,000. Each element of the array A is an integer within the range 0 to 200,000. So we're dealing with a lot of numbers. So we have day 3, because index always starts at 0, minus the first day, gives us a loss. So if the share was bought on day 4 and sold on day 5, the profit of 354. Well, as we all know, figuring out what the problem is half the solution. So let's go ahead and start with our notes. We have to find a profit. If no profit is found, we return 0. Right? Yeah, right here. So we have to find how we can buy something and sell it on another day. And then we just have to return what they need to return the maximum profit. Hopefully I spelled that right. I'm a coder, not a writing major. They would occur if share was bought on day 1 and sold on day 5. So we need to get the difference of day 1 versus 3, 4, 5, 6, and 7. And do that for each iteration. You can use their example here. Whoops. Try and figure out how we can go through this list. So if we bought something for $10 and sold it the next day for $5, that's a loss. And if we buy something for $5 and sold it for $10 the next day, that's a profit. And then we would want to return 5 here. So just working with smaller numbers and a shorter list should help us gain the basic necessity of what this program needs to do. So we want to figure out the maximum difference. That's the one we want to return. We don't care what day it occurred, but we can't say we bought it on day 5 and sold it on day 6. Bought it on day 5, sold it on day 2. Although I'm sure a lot of people on Wall Street wish they could. We can start for X in A. X minus we need to go through this. So maybe instead of A, we just say range the length of A. So we can say that our index of AX minus AX plus 1. So we get the initial value that we're at and the next value. We're going to want to have our profit starting with 0. If we can also have our conditions up here, that might help us. So we need to focus on this. And provided that AFQ is greater than AFP, otherwise the transaction brings a loss. see. So in my head, here's what I'm thinking. If we can just constantly work through and figure out, is this the biggest? If it's bigger than our profit, great. If not, move on to the next one. This should be iterating through to give us what we have. So if A of X is greater than or equal to profit, then we want to update that value. So let's have a temporary variable equal to the difference. Then we'll say if our temp is greater than or equal to profit, and we want to say profit equals temp. And I wonder if that'll be just enough for us to actually get the desired outcome. I think it should be. I'm not too sure. But we know how we do it here. We test and prod. Turn profit. Let's go ahead and run our code and see what we get. All right, already getting an error. We need to, so right now we're indexing out of range, especially for those simple ones. What if we just reverse this so it's X minus 1, and then we get that. Okay. We got the same values here and here. So already we found our first bug. And we're providing negatives, which isn't good. How do we want to handle this? Let's go ahead and print what our X is so we can see what we're dealing with. I really prefer +1 because we don't want to go backwards. One to our length. All right, and I think we're hitting the same error. So we have 0 through 5, which is correct. But we're still not getting the right answer. So if we can say, well, how about we have size equals to length of A. So now we have that. We can change this to be size if X is greater than our size. Let's just say pass. The idea is if our index, our new index is greater, we want to immediately stop because we've hit the last day of trading. Let's see. Maybe if we return profit here. Would that stop us from indexing out of bounds? We still need the +1 for our size. Let's see. Okay, we don't need the +1. Where are we falling? Right here, when we try and index still. We're still trying to index out of range. We might be able to combine these two. So if x is greater than or equal to less than or equal to size, and our temp value is greater than our profit, less than. Do we just need to check that x is less than our size? I think so. Nope. We're going to need that temp value still. Still doesn't solve it. X equals size, we want to stop. We're at the end of the day, no profit to be made. Which means we should stop and we shouldn't have to try and index on that greater. Right? Oh. Equals size. Still indexing out of it. Do we have to subtract 1? Because we're going too far? Closer. But now we're not. Right, because we can't check that last day. And do I have this backwards by chance? Because we're not getting the proper value. We're returning this. So maybe if we do minus a of x, that should give us the proper negatives. Okay, we have 354 as our profit now. Oh, but it's expecting 356. Let's think. Day 1, we buy it. Day 2, we sell it. We're only checking for the next day being sold. Right? Because we need to be calculating, is it best to sell it on the second day, the third day, the fourth day? And then moving on to the next one. I'm not sure. If we have an array of values, we need to check if a single share is bought on a day P and sold on day Q, where 0 is less than or equal to P, which is less than or equal to Q, which is less than N, then the profit of such a transaction is equal to A of Q minus A of P, provided that A of Q is greater than or equal to A of P. Otherwise, the transaction brings a loss of A of P minus A of Q. And we only want to return the maximum profit. It did say something interesting when I reread it. So we have A of Q minus A of P, and the fact that A of Q is greater than A of P. Otherwise, it's A of P. Thanks for the spam. Minus A of Q. Just have otherwise. Which is a loss. Can we go through and just check which days are higher? So if A of Q is greater than or equal to A of P, then we want to know what that difference is. Otherwise, keep going, right? So this is tricky. I think we can do it in a for loop and just a couple if else. What am I stuck on? Let's go ahead and comment this out. This is right. This is right. This is wrong. Oh, are we returning one less? We need to figure out what we're doing wrong. This has to be missing something. Or x in size minus 1. We're going to have our first day equal to a indexed on 0. And then we can focus on figuring out moving through. Let's double check that we're going through the right range. We have size minus 1, so if the length is 5 or 6 days, we want to go through all 6 days. We're only getting the immediate next day, but if we can do, maybe instead of range, we do our index on the first, which is the second day to the end. And we just keep comparing it to the first day. So if we say something along the lines of, if x is greater than or equal to our first day, then we want to do profit, which would be the maximum difference set to our value profit, which is x minus first day. I think that's closer to what we're trying to get at. So we don't want the immediate next day. So how do we update first to be our new value? How do we calculate the difference of each day and making sure that we have the maximum profit? Don't have size anymore. I don't think we need that. Else, return 0. All right, we took a step backwards. It works for this case, but not for the example case. Because I think we're still just subtracting that from the first day, but we want to go through each day. Array A consists of n integers. It contains a daily price of the stock share over the period. If a single share was bought on day P and sold on day Q, where 0 blah blah blah, such that the transaction that should give us what we're looking for. And we're iterating through the rest of the array here. We're checking that the maximum for profit but we're not updating the profit value, are we? So if X is greater than or equal to our first day, then we want to say that profit equals X minus first, and maximum profit is equal to that. So if we have our maximum profit equal to 0, because we can just return that, song but never used. So you want to make sure that we return the maximum profit that we can get, and since we started with 0, that should be the right answer. We update profit using X minus the first day. Let's see. And we're still getting 0. Are we not properly iterating through? Oh, we're returning 0 right there. We need to update our minimum price, or first with the new one. So we'll call this day. And if it's set to that, just to help us better contextualize it, should be able to update our day with the new value. Because we're checking if X is greater than the day, then we can update the maximum profit. Otherwise, it's a new day. Right? Okay. All right. I think we're properly doing it now, because now we have 0 when we don't make a profit. We have 5 when we do make a profit, and we are getting the right value now. Perfect. I think we can go ahead and submit this. Let's see how many tests we get through. Fingers crossed. This would be a great way to start Monday. Session has ended. Fingers crossed we get at least a passing grade. But using that maximum built-in function it will go through that array, finding the maximum difference for us. And since we update each day, we can't go back in time. We can only move forward for now. Come on, fingers crossed. Passing grade. Give me something. Anything. I'm not a stockbroker. But yeah, our max profit starts at 0. Our day is starting on day 1. So for the value of the next day to the end, if that day is greater than the current day that we found, our new profit is that minus the value of the day. And then we just find the maximum. If it is the maximum profit. So it needs to be higher than the current profit. And then it will update. Otherwise, change the day to the next one. Taking some time. Any minute now. Well, at least the stream's still alive and well, it looks like. Oh, ooh. Ouch. That one hurts. Our correctness, we got 40. Performance, very bad. So our task score is 33. That's not a passing grade. What did we fall short on? Simple, empty. Empty and 0 to 200,000. Index of 0. List index is out of range. 2 increasing sequences. Got 2,000, expected 99,000. Jeez. All right, so for this first arrow, we can say, you know, the length is 1 or less. Just return 0. This one I'm not sure about. Got 3, expected 7. I think we're going to have to go back and continue trying this one. I just want to at least see if fixing that little bug of if we only have 1 day, how greatly does that increase our score? Shoot. A duck. What do we have? I always forget to save it before we submit. But if we do our day, okay. I kind of remember. It's if length of our array A is less than or equal to 1, return 0. Else we can say that our day equals A indexed on 0. Our maximum profit is equal to 0 for X in our array from 1 to the end. Right, because if it has to be greater than or equal to 1. Means that there's at least 2. Now we can go ahead and say if X is greater than or equal to our day, we'll do the profit equal to the day minus, okay, our profit is X minus our start date. And then we can do our max, max profit equal to the max of max profit, comma, X minus day for the value of that day. Otherwise, we want to update our day to the new day. After that, we returned maximum profit. Go ahead and run that. Okay. Let's go ahead and save this. Profit is assigned but never used. Is this supposed to be just, oh, since we're already doing that here, we can just say profit equal. Here we go. We want the bigger value because we're just subtracting the day. Okay, go back to where we were. Let's go ahead and submit this task. See if we can get updated score. Anything better than 33 would be great. No, I guess we could have just thrown in our example of a single day, because that was one of the contingencies here. I wonder why it takes so long to iterate through. Ah, boy. Any minute now. Any second. We're going to get that value back. We're going to be rolling in that maximum profit. Hopefully. These programs that test people's ability to program is crazy. In fact, I think I saw AI assistant chat. I wonder if that means that it's available to the person that's being tested. If we get a pass, I think we can go ahead and jump into our containerization lesson for the day. Which is the main goal I want to get to. I've used Docker in the past. I've been able to, it's really good when you're just testing programs and even wanting to host a website or web app. Making sure that it runs in a Docker container means it should be able to run on anyone's computer. This is how, like, a lot of developers deal with containers, I feel. If they can copy the Docker file, it should set up everything accordingly. And I think that's how a lot of Try Hack Me or Hack the Box works. It's all containers that run the vulnerable web app they want you to play through. We'll see. I also need to run to do a quick errand before we get into that lesson. I just wanted to see if we could get a better score first, that's all. Let's also make sure that our simple chat app is still working. Ooh. Ooh, that's not sound good. Spin that up again. I think I might have mentioned it before. I'm hoping to open source this little program so other people can use it without having to pay for subscription to Streamlabs. Although I do use Streamlabs. Let's see. We want to activate our virtual environment. Python. How does that sound? Dude. Oh. Definitely gotta work on that. I wonder if that's me or if that's something else causing that issue. Could be my internet. Oh, there we go. 100%. That was it? That's all we needed to fix was, like, if it's an empty list? I guess that was it. All right, sweet. And with that, we're going to take a short break. When I get back, we're going to hop into containerization. All right, sit tight. And we're back. All right. So I feel pretty good about this test. I'm glad we were able to go up from 33% to 100. Amazing that we were losing that much on correctness and our total score just because we weren't checking for an empty list. That should have been our first thing to think about. But that's why it's important to reread the instructions, take our time, and build upon what we know and what we want to get out. Also trying to get our minds around thinking about edge cases all the time. All right, now for the part everyone's been waiting for. Let's go ahead and switch gears into some cybersecurity. We'll be doing the containerization, intro to containerization room for Try Hack Me. And yeah, let's see if we can learn something new today. So, this room is the first series explaining popular technology of containerization. When we complete this room, we'll be able to say what a containerization is and what containers are, where and why containers are used, a fundamental understanding of popular container technology, just like Docker, what makes Docker so popular, and how they work. Sounds good. Let's get started. In computing terms, containerization is the process of packing an application and the necessary resources, such as libraries and packages, required into one package named a container. The process of packaging applications together makes applications considerably more portable and hassle-free to run. This is what I was mentioning earlier. Being able to say it works on my machine doesn't mean it's 100% good. As a developer, if you're developing a web application or whatever you're making, while you're working on it, you might have to install some special libraries and have that part just added. So using containers allows us to wrap all of it up in a nice little bow and send it off to other people to just run right off the bat. Hopefully. Modern applications are often complex and usually depend on frameworks and libraries being installed on a device before the application can run. These dependencies can be difficult to install depending on the environment of the application, create difficulty for developers to diagnose and replicate faults, as it could be a problem with the application's environment, not the application itself. This can also often conflict with each other. For example, having multiple versions of Python to run different applications is a headache for the user, and an application may work with one version of Python and not another. So this allows us to make sure we're installing the right version of Python and it's using the proper built-in functions and libraries and all that other good stuff. Containerization platforms remove this headache by packaging the dependencies together and isolating. Note, this is not to be confused with security isolation in this context. The application's environment. If the device supports the containerization engine, a user will be able to run the application and have the same behaviors. It just helps eliminate a lot of that headache of like, well, I'm using Python 2. Well, I only have Python 3 installed. Well, now you have to install Python 2. Stuff like that. So we can see we have 3 containers. We have the Docker engine, and then the host computer, and then the physical computer. Well, the host operating system, and then the physical computer. In the screenshot above, we can see how 3 applications and their environments, such as dependencies, are packaged together and do not directly interact with the physical computer, but rather the containerization engine. In this case, it's Docker. So we have our app and the environment for each of these. Normally, when you run an application, it's just from your OS to physical computer or whatever. We will come to discuss precisely how containers isolate from one another, but for now, it's important to understand the isolation is a core feature of the containers. However, it is worth noting that containerization platforms make use of the quote namespace feature of the kernel, which is a feature used so that the processes can access resources of the operating system without being able to interact with other processes. Good to know. The isolation offered by namespaces adds a benefit of security because it means that an application is in the container is if an application in the container is compromised, usually, unless they share the same namespace, other containers are unaffected. So that's sort of what I was hinting at earlier, being able to break out of the container and touch other apps that might be running on the same space. Alternatives, such as virtual machines, will require a whole operating system being installed to run applications. It takes up large amount of disk space and other computing resources like CPU and RAM. All right. What is the name of the kernel feature that allows for processes to use resources of the operating system? Namespace. Nice. In a normal configuration, can containers interact with each other? I'm gonna say nay. The nays have it. All right. I promise I'll try to keep the sales pitch relatively short. Docker is relatively hassle-free, extensive, and open source containerization platform. The Docker ecosystem allows applications, which are images, we'll come to in this room later, to be deployed, managed, and shared with ease. Moby Dick. Working on Linux, Windows, and Mac OS, Docker is a smart choice for running applications. Applications can be published as images and shared with others. All that is required is pulling, which is downloading, the image and running it with Docker. Sure. I like how easy it makes this sound. Docker employs the same technology used in containerization to isolate applications into containers called the Docker engine. The Docker engine is essentially an API that runs on the host operating system, which communicates between the operating system and the containers to access the system's hardware. CPU, RAM, network, disk, all that good stuff. Because of this, the Docker engine is extensive and allows you to do things like connect containers together. For example, a container running a web app and another one containing container running a database. Sounds easy enough. We can export and import applications, which is those Docker images, transfer files between the operating system and the container. All good benefits. Docker uses the programming syntax YAML to allow developers to instruct how a container should be built and what is run. This is a significant reason why Docker is so portable and easy to debug. Share the instructions and it will build and run the same on any device that supports the Docker engine. Very key there. Like I said, when you're on a development team, being able to send over the updated Docker file, they can just run it and it should react the exact way that it's running on your computer. The Docker engine allows containers to be orchestrated, meaning that multiple containers can be built as part of a group, allowing containers to communicate with each other. For example, one container running the web server, another one containing the database, so they can communicate back and forth. If you have like a user account or very important information, having those Docker containers talk to each other to share that information. So what does an application become when it is published using Docker? An XXXXX. When it is published using that. An image? There we go. What is the abbreviation of the programming syntax? YAML. We're just cruising through this. Originally created by Solomon Hykes in 2013, Docker is open source and has become well-renowned name within containerization. Docker started as an internal project for .cloud, a PaaS provider, where it was then showcased in PyCon in 2013. Wow, that old. I didn't realize. And then quickly made open source. While containerization's original concept started in 1979 with Unix v7, Docker has made containerization a popular technology since its release in 2013. Docker's popularity is due to making the benefits of containerization accessible and modern. As of April 2022, it's fair to say Docker is extremely popular. To be precise, 13 million developers, 7 million applications made and ready to use with Docker. 13 billion applications are downloaded monthly, and this is just from their official repository. What year was it originally created? 2013? Okay. Where was Docker first showcased? That would be PyCon. And what version of Unix? Version 7. Sweet. Cruising through this. If it hasn't been said enough, here's another attempt. Docker is an agile, convenient, and extensive means of deploying an application. Let's explore this in detail in the headings below. Docker is free. The whole ecosystem is free to use and open source. While business plans exist, you can completely download, use, create, run, and share images. Docker is compatible. The Docker platform is compatible with Linux, Mac, and Windows. Because of how containerization works, if a device supports Docker engine, you can run any container regardless of the application or dependencies, if you have the resources available too. Docker is efficient and minimal. Docker is an efficient way to isolate applications in comparison to alternatives such as virtual machines. This is because Docker engine runs and interacts with the host operating system, and containers do not run a fully fledged operating system for each container. For example, containers can share a minimal operating system image, meaning you only need to store it once. Minimal Ubuntu image is 100 megabytes. Wow. That was the size of my first USB drive. It can be stored once and used multiple times. Compare this to Ubuntu's server image, about 1 gigabyte after a fresh install per VM. And that adds up. Each image that you have, each version, each dependency that it needs to install, 1 gig can quickly become 100 gigs, especially in a corporate environment. Docker is easy to get started with. The Docker developer documentation is very well documented, with lots of articles, working examples, and answered questions on the internet. Chances are, if you want to do something in Docker, someone has already asked about it or done it. The syntax to get started with Docker is easy to pick up. You can start with your first container in no time. The fact that there are Docker images for all sorts of applications already published helps. Docker is easy to share with others. So, talking about that portability again, using those images to upload and download and being able to update that for whatever your need is for that container. Just an instruction manual. These images can be exported, shared, and uploaded to both public and private repositories such as Docker Hub and GitHub. The image can be run on anything that supports a Docker engine, as long as the syntax is valid. Makes sense. Docker is minimal, like we covered. These Docker images are minimal and will often use many core and luxurious tools and packages in a container that are missing. While this can look like a disadvantage, it is in fact allows containers to be built exactly how the developer wishes. Better security, knowing exactly what runs within a container can reduce the risk of unnecessary packages becoming vulnerable and posing a security risk. Docker is cheap to run. Running containers is usually a cheaper option than running virtual machines. This is especially noticeable in cloud environments where CPU and RAM and disk space are expensive. For example, you can quite happily run a few containers on a single $5 cloud provider VPS, whereas you will not be able to run a virtual machine. This is due to the fact that running virtual machines requires hardware, supports virtualization, which is only found on costly tiers of a cloud provider, if at all. Virtual machines require lots of memory and disk space, as you're running separate operating systems on top of a physical machine. So it just keeps building and building and building. Are you sold yet? All right. Namespaces essentially segregate system resources such as processes, files, and memory away from other namespaces. Every process running on Linux will be assigned two things: namespace and a process identifier, a PID. Namespaces are how containerization is achieved. Processes can only see other processes that are in the same namespace. No conflict in theory. Take Docker, for example. Every new container will be running as a new namespace, although the container may be running multiple applications and in-turn processes. Let's provide the concept of the containerization by comparing the number of processes there are in a Docker container that is running a web server versus the host operating system at the same time. So here we can see, the process of the ID of 0 is the process that is started when the system boots. Process numbers increment and is started by other processes, so naturally the next process ID is 1. This process is the system init. For example, the latest version of Ubuntu uses system D. Any other processes that runs will be controlled by system D, our first process. We can see process 1's namespace of the operating system to escalate our privileges. While containers are designed to be namespace to isolate from each other, they can instead coincide with the host computer's processes. This gives us a nice opportunity to escape. Already we're looking into container escapes. I like it. So here we have PID 1, and we're running bin and Apache in the foreground. What command can we use to view a list of application running processes? PS aux. All right. Getting into the practical. Now we're talking. Let me make sure that we have our virtual machine up and running. I think we're going to need it. It's good to have running in the background just in case anyways. Or maybe we can use it for one of our other walkthroughs. So I'll go ahead and get this kicked off. Deploy the static site attached to a task. Okay. Probably should check that before starting. Assemble the layers of the container to retrieve the flag. So we have our application. Then we have container engine there. Physical machines there. We have our physical machines operating system and our container. All right, application is being shipped. Boom, baby. Now we know about containers. But I think we can keep going. Let's go ahead and dive into Docker. This is the one that's most popular. There's other versions and other container applications that are used a lot. Kubernetes is one of them. But for now, we'll just focus on Docker. In this room, you'll get first hands-on experience deploying and interacting with Docker containers. Right. Please note it's strongly recommended that you are at least familiar with basic Linux. All right. Additionally, it's important to remember you will need internet connectivity to pull Docker images. Hopefully, they're not too big, but like we saw, should be fairly straightforward. All right. go ahead and get started. Basic Docker syntax. Docker can seem overwhelming at first. However, the commands are pretty intuitive, and with a bit of practice, you'll be a Docker wizard in no time. So the syntax for Docker can be categorized into 4 main groups: running the container, managing and inspecting containers, managing Docker images, and Docker daemon stats and information. We'll be breaking down each of these categories in this task. Oh, boy. So Docker pull. Before we can run a Docker container, we first need an image. Recall from intro to containerization room. These are the images are instructions for what a container should execute. There's no use running a container that does nothing. In this room, we will use the Nginx image to run a web server within a container. Before downloading the image, let's break down the command and syntax required to download the image. So we use the command docker pull to provide the name of the image to be downloaded. Docker pull nginx using default tags latest, pulling from the library nginx, and then download newer image of nginx, the latest. Seems pretty straightforward. By running this command, we are downloading the latest version of the image. Images have these labels called tags. These tags are used to refer to the variations of an image. For example, an image can have the same name but different tags indicating a different version. I've provided an example of how tags are used within the table below. So we have our Ubuntu Docker image, the tag with the latest. Docker pull Ubuntu is the same as Docker pull Ubuntu latest. So it's just making sure whatever version you're using is the right version. Always having the latest might not be the greatest thing. For example, we have 22.04, 20.04, and 18.04. This helps a lot with especially legacy applications. Here we go. It's worth remembering you don't always want to pull the latest. The image is quite literally the latest in that sense. It will have the most recent changes. This could either fix or break your container. So when specifying a tag, make sure you include a colon between the image name for the tag. So we have Ubuntu 22.04. And don't forget about tags. We'll return to that in the future. Docker image X, Y, and Z. Docker image command with the appropriate option allows us to manage the images on our local system. To list available options, we can simply do Docker image to see what we can do. I've done this for you in the terminal below. So they use the command Docker image. We can see Docker image and then whatever command we want, whether it's build, history, import, inspect, all these other good stuff. In this room, we are going to cover the following options of Docker image: pull, ls, rm, and build. So this will be building our container, removing the image from our host, listing all the images, and pulling it, which is downloading, which we've already seen. So we have Docker image ls. So these are the images that are saved locally that we can reuse. We can see some of the information for these 2 images on the system. We have Ubuntu version 22.04. It has its own ID, when it was created, and how big it is. We also have Nginx, grab the latest, and all that other good stuff. Docker image rm. If we want to remove an image from the system, we can use Docker image rm along with the name or image ID. In the following example, I'll remove Ubuntu image with the tag 22.04. So Docker image rm Ubuntu 22.04. This helps if you're trying to clear up some space or if an image is no longer needed. So they went ahead and removed that, making sure that the hashes match up. Docker image ls. So now we can see only Nginx is available. If we wanted to pull a Docker image, what would our command look like? Docker pull, and then the name of whatever image. We wanted to list all the images on a device running Docker. What would that look like? Docker image ls. All right. Let's say we wanted to pull an image named try hack me. What would that look like? Should be Docker pull try hack me. All right. What if we want the version 1337? Docker pull try hack me colon 1337. Delete. Running your first container. Oh boy, here's where it gets good. Let me just make sure they got some. Docker run command creates running containers from an image. This is where commands from Dockerfile, as well as our own input at runtime, are run. Because of this, it must be some of the first syntaxes you learn. The command works in the following way. We have Docker run, options, image name, the command that we're running, and the arguments that are needed for that. Docker containers can run with various options depending on how we will use the container. This task will explain some of the most common options that you'll want to use. First, simply running a container. Docker run, and then our command. An image name hello world. Interactively, by providing the -it switch in the options command, will allow us to interact with the container directly. Going to spawn a shell within the container by providing bin bash as a command part. This argument is where you'll need to place the commands you want to run within the container. So, to achieve the above, my command will look like the following. Docker run -it hello world bin bash. And here you can see that we're running as root on this Docker image, or whatever the host name that is generated. We can verify that we have successfully launched a shell because our prompt will change to another user account and hostname. The hostname of the container is the container ID. I thought so, I just didn't want to jump the gun if I was wrong. This can be found by using Docker PS. For example, the terminal above, our username and host are root at that hostname. Running containers continued. Oh boy. So we have all these other options. -d. This argument tells the container will start in detached mode. This means that the container will run in the background. Run -d hello world. This argument has two parts, it. The I means it will run interactively, and T tells Docker to run a shell within the container. We will use this option if we wish to interact with the container directly once it runs. -v. This argument is short for volume. It tells the Docker to mount a directory of file on the host operating system to a location within the container. The location these files get stored is defined in the Docker file. So this helps you share files between your host machine and whatever the container is. So we see -v, our host operating system directory, colon, the container directory. So it's first our host, and then it's the containers, and then followed by our image. -p. This argument tells Docker to bind a port on the host operating system to a port that is being exposed in the container. You would use this instruction if you are running an application or service, such as a web browser, in the container and wish to access the application service by navigating to the IP address. So Docker run -p 8080 web server. So this will bind your local host's IP on port 80 and combine that with the container's port 80. 80 is how we use browsers and web servers, HTML and all that good stuff. RM, --RM. This argument tells Docker to remove a container once the container finishes running whatever it has been instructed to do. Docker run --RM hello world. And we have --name. This argument lets us give a friendly, memorable name to a container. When the container is run without this option, the name is 2 random words. Okay, Docker run --name hello world. That helps us manage them a little bit better. These are just some of the arguments we can provide when running a container. Again, most arguments we need to run will determine on how the container is built. However, arguments such as --RM and --name will instruct Docker on how to run the container. Other arguments include, but are not limited to, telling Docker what network adapter we should use, what capabilities the container should have. This is covered in Docker Rodeo. Might have to try that one next. Or storing a value in an environment variable. If you wish to explore some of these arguments, we can review the run documentation. Listing running containers. So we use the command docker ps, and this will give us the container ID, the image that's running, the command that it has, when it was created, the status, ports that are being used, and other names it might have. This command will show us all that good information. To list all containers, even stopped, you can use docker ps-a. So it's probably docker ps all. So we can see previous containers that we were using. GoBuster on cinematic, the command that's being used, and whether it's running or not. Cool. What command that we want to use if we want to run a container interactively? Docker run -it. Boom, boom. What would our command look like if we wanted to run a container in detached mode? Docker run -d. We want to run a container and bind a web server on port 80. Docker run -p 8080. Right? Sweet. Can we list all running containers? Docker ps. And how will we list all the containers, including the stopped ones? That was docker ps-a. Perfect. Docker files. All right. Where all the magic happens. Let's see. Docker files play an essential role in Docker. Docker files are formatted in a way which essentially serves as an instruction manual for what the container should do and ultimately assembles a Docker image. You use Docker files to contain the commands the container should execute when it's built. To get started with Docker files, we need to know some basic syntax and instructions. Docker files are formatted in the following way. We have our instruction followed by the argument. All right, let's cover some essentials. We have from, run, copy, work directory, cmd, and expose. So the from instruction, this sets a build stage for the container as well as settings for the base image, with operating system. All Docker files should start with this. So from Ubuntu. All right, run. This instruction will execute commands in a container within a new layer. Run whoami. So right off the bat, we have from Ubuntu run whoami. So when the image starts and it's running, it will execute this command. Copy. This instruction copies files from a local system to the working directory in the container. Okay. The syntax is similar to a cp command. Copy our home directory from our app, working directory, or work dir, This instruction sets the working directory of the container, similar to CD on Linux. CD what, you might ask? Nice try. So this sets the root of the file system in the container. CMD. This instruction determines what command is run when the container starts. We'll use this to start a service or an application. So CMD bin shell with our script.sh. Expose. This instruction is used to tell the person who runs the container what port they should publish when running the container. Expose 80. Tells the person running, make sure to bind 80 to port 80 of the container. Now that we understand the core instructions of the Docker file, let's see a working example. But first, let's explain what they want the container to do. Use the Ubuntu operating system as a base, set the working directory to the root of the container, and create a text file called hello-world.txt. Docker files are just like recipes, but for computers. We can see that the pound sign allows us to make comments. So from Ubuntu version 22.04, set the current working directory to root and create a hello-world.txt. So it runs the command touch hello-world.txt. Remember, the commands that you can run via run instruction will depend on the operating system you use in the from instruction. So I guess that means if you're trying to run Linux, you have to make sure that you're actually running Linux. You're not trying to run Windows commands. Okay. Building your first container. Once we have a Docker file, we can create an image using Docker build command. This command requires a few pieces of information. Whether or not you want to name the image yourself, we'll be using the -t argument. The name that you are going to give the image, the location of the Docker file you wish to build with. Straightforward enough. In this scenario, relevant command, let's say we want to build an image, filling out the two required information that we listed above. Using the -t argument, name of the image, and the Docker file is located in the working directory. Okay? So the Docker command should look like docker build -t hello world period. They're using the dot to tell Docker to look in the current working directory. If we have filled out the command right, we'll see Docker starting to build the image. So we have our docker build -t hello world period. You can see some of the steps. Grabs from, pulls from our library, grabs the Ubuntu image that we have already downloaded, checks if there is a newer image for that version 22.04. Working directory, run this command, successfully built and tagged hello world with our latest image. Sweet. Then if we use the command docker image ls, we can see that it was just built about 2 minutes ago. Whatever base operating system you list in the from instruction in the Docker file will also be downloaded. This is why we can see two images, hello world and Ubuntu. All right. We can refer to running your first container task to remind you how to start a container. I think we got it. Leveling up our Docker file. So we want to use Ubuntu 22.04, install Apache 2 web server, add some networking. Since it's a web server, we'll want to be able to connect to the network somehow. We'll use the expose instruction, telling the container to expose port 80, tell the container to start Apache 2 as a startup service. And containers do not have service managers like systemd. Systemd. I always say systemd for some reason. This is by design. It's bad practice to run multiple applications in the same container. For example, this container is for Apache 2 web server and the Apache 2 web server only. using the benefit of containerization, making sure they're all separate is why we're using Docker in the first place. So from Ubuntu, run apt-get update -y. So we ensure we have the latest version of Apache 2. Run apt-get install Apache 2. Yes. This -y is just saying yes to anything that pops up. Do you want to install this? Yes or no. Expose port 80. And then we'll want to run the command in the container Apache 2 CTL-D foreground. For reference, the command to build this would be docker build -t web server period, assuming that the Docker file is in the same directory where you can run the command from. Docker run -d our name web server, port 8080 web server. Cool. Cool. Optimizing our Docker file. There's certainly an art to Docker, and it doesn't stop with the Docker files. Firstly, we need to ask ourselves why it is essential to optimize Docker file. Bloated Docker files are hard to read and maintain and often use unnecessary storage. For example, you can reduce the size of a Docker image and the build time using a few ways, only installing essential packages. What's nice about containers is that they're practically empty from the get-go. We have complete freedom to decide what we want. Removing cached files such as apt, cache, or documentation installed with tools, the code within container will only be executed once on build. So we don't need to store anything else for later. We're not actively using this to continue. We're not developing inside the container. We're developing outside the container. Using minimal base operating systems in our from instruction, even though operating systems for containers such as Ubuntu are already pretty slim, consider using an even more stripped down version, Ubuntu 22.04-minimal. For our example, using Alpine, which can be as small as 5.59 megabytes. Wow, that is tiny. Minimizing the number of layers. I'll explain this further. Okay, so we have our before Docker file. Grab the latest Ubuntu, update, upgrade all the things, install Apache, and install some tools that we need. All right, and now they can just do from Ubuntu, grab the latest, run our update, upgrade, install Apache, and install the net tools. Gotta love those one-liners. Docker build -t after period. So we're sending the build context to Docker daemon, and we can see our step 2 running all these commands and running. So from Ubuntu and running this chain of update, upgrade, install, and run, or update, upgrade, install, and install other tools. So what instruction would we use to specify the base image of the container should be using? That's our run. The instruction to tell what to run. Ooh, it's not CMD. Run. There we go. The command to build an image. Just build. Pretty intuitive. And let's say we want to name the image. What argument will we use? So -n. Shoot. We want to name the image. What was that specific? -t. Because we're giving it a tag. Or title. Let's first understand what Docker Compose is and why it's worth understanding. This is what I always get confused on. So far, we've only interacted with containers individually. Docker Compose, in summary, allows us to use multiple containers to interact with each other when needed while running in isolation from one another. You may have noticed a problem with Docker so far. More often than not, applications require additional services to run, which we cannot do in a single container. For example, modern dynamic websites use services such as database and a web server. For the sake of the task, we'll consider each application as a microservice. All right. While we can spin up multiple containers or microservices individually and connect them, doing so one by one is cumbersome and inefficient. Docker Compose allows us to create these microservices as one singular service. So Docker Compose will allow us to have all these containers spun up and connect to each other. Just more instructions for the recipe. Before we demonstrate Docker Compose, let's cover the fundamentals of using Docker Compose. We need Docker Compose installed. It doesn't come with Docker by default. Installing it is out of scope for this room. It changes depending on your operating system and other factors. We need a valid Docker Compose YAML file. Come back to that shortly. Fundamental understanding of Docker Compose is to build and manage containers. We have up, start, down, stop, and build. Up, so Docker Compose up, will recreate/build and start the container specified in the compose file. This command will, then we have the Docker Compose start. This will start, but requires containers already being built, the containers specified in the compose file. So if we already have our container built, we can just say start that container. Down. This command will stop and delete the container specified in the compose file. Stop. This command will stop, but not delete the container specified in the compose file. And build. This command will build, but not start the containers specified in the compose file. Do you have any familiarity with this? It's usually Docker Compose build, Docker Compose up, Docker Compose start. I think it's that order. Or sometimes you just have to do Docker build, Docker start. Or Docker Compose build, Docker Compose start. See how I'm already confused sometimes? Showcase of Docker Compose. So let's look into it ourselves. In this scenario, I'm going to assume the following requirements. An e-commerce website is running on Apache. The website stores customer info in a MySQL database. Now, we could manually run the two containers via the following: creating Docker network, create e-commerce, which is our name of our image, Docker run with port 8080, name of the container, -- net, e-commerce web server, Docker run, database, e-commerce web server. And this is probably -- net, so they can both talk to each other. So here we have an illustration. That's fine. Instead, we can use Docker Compose up to run these containers together, giving us the advantage of one simple command to run both of them. These two containers are networked together, so we don't need to go about configuring the network, and makes this extremely portable. We can share our Docker Compose YAML file with someone else, and they can get the setup working precisely the same without understanding how the containers work individually. This makes it easy to maintain and change. We don't have to worry about specific containers using probably outdated images. All right, Docker Compose files 101. We have version, services, name, build, ports, volume, environment, image, and networks. Oof, man. So, Docker Compose YAML version. This is placed at the top of the file and is used to identify what version of the Compose the Docker Compose is written for. Example 3.3. We have services, which marks the beginning of the containers to be managed. We have name, replace value. This instruction is where you define the container and its configuration. Name needs to be replaced with the actual name of the container you want to define, such as web server or database. We have build, directly building the container. We have ports, which will be our 8080. Volumes, that's our shared file system. Environment, this instruction is used to pass environment variables, passwords, usernames, time zones. MySQL root password hello world. We have our image. This is the image the container should be built with. MySQL latest. And networks. This instruction defines the network the containers will be a part of. Containers can be part of multiple networks. Good to know. So we have our network called e-commerce. Let's go ahead and jump down. We have our version, services. We have web, which is to build our web. Make sure it's networked to the e-commerce network and exposes port 8080. Then we have our database, which is MySQL latest, connected to network e-commerce with these environment variables. Then we have our network of e-commerce. Makes sense? I want to use Docker Compose to start up a series of containers. Should just be up. All right. We want to delete a series of containers. That should be down. And what is the name of the Docker of the .yaml file that Docker Compose uses? Docker Compose Docker-compose.yaml. There we go. Now we're on it. Whoop. All right. This task will explain how Docker interacts between the operating system and container. When you install Docker, there are two programs that get installed. We have the client and the server. Docker works in a client-server model. Specifically, these two programs communicate with each other to form the Docker that we know and love. Docker achieves this communication using something called a socket. Sockets are essential feature of the operating system that allows data to be communicated. For example, using a chat program, we have two sockets. Socket for storing a message that you are sending and storing a message that someone is sending you. The program will interact with these two sockets to store or retrieve the data within a team. The socket can either be a network connection or what is represented as a file. What's important is to know that sockets is how they allow for inter-process communication, IPC. Make a note. This simply means that processes on an operating system can communicate with each other. In the context of Docker, the Docker server is effectively just an API. Okay. Docker server uses this API to listen for requests, whereas Docker client uses the API to send requests. Seems straightforward enough. So we have Docker run hello world. The Docker client will request the Docker server to run the container with the image hello world. Now, while the explanation is fairly basic, it's essential to the premise of how Docker works. You have our client, hey, making container using this info, Docker socket, and then the Docker server will say, okay, I'll go ahead and run that for you. Interesting. What's interesting is that because of this, we can interact with the Docker server using commands like curl or an API developer tool such as Postman. I've used that in the past. Now, using this is out of scope for this room, but we'll demonstrate basically. So reaching the Docker rodeo .tryhackme port 5000 version 2 catalog will give us some of the repositories. All right. What does the term IPC stand for? Inter-process communication. Nice. What technology can the Docker server be equated to? API. All right, now we're getting into the practical. Let's go ahead and start that machine and making sure that everything's up and running. Stand by. We'll just go ahead and use their attack box, since hopefully it has everything installed that we need to use. Connect to the machine. What is the name of the container that is currently running? And use Docker to start a web server within the web server image. No quotations. You'll need to run the container with port 80. After starting the container, trying to connect to whatever our URL in the browser was the flag. All right. Seems pretty straightforward. I think in a future stream, we'll go ahead and walk through setting up the damn vulnerable web app using Docker. This makes sure that all the vulnerabilities are properly set up and in place. This will give us better access to a lot of the exercises. The problem I've been running into is some of the services are outdated. So, oh boy. All right. So connect to the machine. What is the name of the container that's currently running? Anyone remember? We want to run Docker PS. See what's currently running. So we have Cloud Island. Its command is tail-f dev null, created 2 years ago, and it just turned on. Cloud Island. Boom, boom, baby. Try connecting to this. So let's try and curl HTTPS 10 dot, 10 dash 10 dash 169 nice 203.p.thm.labs.com. Hopefully this will just give us the full website. If not, we might actually have to spin up our local VM, connect through the VPN, and try and access this site. For this room, I'm hoping we don't have to. This does seem to be a bit slow. We still running? Yeah, we're still good. I guess in the meantime, I'll get our virtual machine up and running. Let me know if we're able to see the HTML yet. Okay. Hello? Anybody there? If that's not going to work for us, we'll do it ourselves. We'll do it live. Go ahead and hide that. Pull up our Kali box. We have our VPN running. And now we can open up an instance of Firefox. Make sure to copy our link. We can just open a new tab for now. 502, bad gateway. We are running. You'll need to run the container with port 80. Oh, I wonder use Docker to start a web server with the web server image. So we have to start up our Docker container. We jumped the gun. Go ahead and pull this back up. So Docker, well, let's see what local files we have. We have our Docker file. We remember what our command is. Docker run cloud island -p 8080. Could have sworn. Docker run cloud island. We didn't use the right port to share. So what was our command? Docker run -p8080. Could have sworn. Invalid option. Status up 15 seconds ago. Oh, maybe we have to bring it down and bring it back up. It exposes that properly. Let's go ahead and cat our Docker file. All right. From Ubuntu, run our update, install Apache, echo, congrats, your flag redacted, and then in the foreground. All right. So what are we missing when we're trying to run our image? It says expose 80. So let's try Docker run -d -name, which is our cloud island -p 8080. Well, that's embarrassing. Docker run requires at least one argument. Web server. Okay. There we go. Now we're properly running. And if we go ahead and pop over to our Kali box, you can see I refreshed the page. Now we have our flag. Try hack me web server container. All right. Now we can go back and submit our new flag. Submit. And we did it. We completed our intro to Docker. Perfect. Right on time. I think that's going to do it for us today. Hopefully everyone learned something new. I know I did. It's always nice to have a refresher on Docker every now and then. Make sure to like, comment, subscribe, follow me for more. Hopefully I'll be back on tomorrow and we can work on getting a set schedule so more people can tune in and learn more. I'd like to try and see if there's any fun Docker escapes that we can practice and test. Otherwise, maybe we'll go ahead and walk through that damn vulnerable web app setup using Docker to make sure we have the exact version that's vulnerable to common attacks. All right. Thanks to everyone for tuning in, and I'll see you next time. All right. Peace out.